It's either true or false. In this house, we obey the law of the excluded middle. I'm Ray Myers. Welcome to Craft versus Cruft. Now, last week I had a video called Theorem Provers Are Refactoring Tools, which was exploring the potential of techniques used in proof assistants, which are used to help us prove mathematical theorems and to formally verify code, usually to a given specification. The potential of those kinds of tools to help us with code refactoring, which is trying to improve the quality, the internal quality of code without changing its external behavior. Today I'm also going to be using a theorem prover, one called Lean, which I actually haven't used before, but it's quite interesting. And this won't be as speculative a topic. It'll be going back over some computer science fundamentals, actually. We're going to show laws of Boolean algebra, which are used to simplify Boolean expressions, for instance, which in its own way, that is code refactoring at the end of the day. This is inspired by a great comment I got on that last video by, I want to say, Maitis. Not quite sure the region they're from, so sorry about the pronunciation if that's not it. They suggested that it would be nice to understand at a particular point in that video why I was choosing the rewrites that I was choosing. And I think this is where I'm glad people were able to make head or tail that video at all, because there were some really advanced concepts there, and I tried to make it digestible, but it is really easy to just forget when you're relying on some bits of knowledge. And I've been doing Boolean simplifications over the course of working with code for so long that I've kind of forgotten there's anything even to learn. But there was a time when I was taking that class too. That said, there are already a lot of people teaching about Boolean algebra. It's fairly easy to find. I will link a couple. This is, for example, looks like a perfectly serviceable YouTube playlist on it. I particularly, in Boolean logic, I love Carnot maps. When you get to that part, that made a lot of things click for me. But I'm not going to try to go back over it the way it's traditionally taught. Lots of people have done that better than I'm going to do it. But I would like, because it is 2024, say it with me if you like, the year of formal methods, I'm going to go back over those laws of Boolean algebra and encode them in a theorem prover, which I find to be a very nice exercise. Now, for the last episode, I'm just going to redo the segment of it that relied on knowledge of Boolean algebra. Now, this is code from a version of the Gilded Rose refactoring exercise that has been written in a dialect of Common Lisp, in particular, a purely functional one. Not really the subject today, but I was specializing this version of this function so that it would only handle this item name called aged brie. So the first step there was I'm going to set, if you compare name to aged brie, that should be true, or it's T in this Lisp dialect. So apply that, and then if you compare it to any other thing after that, we've already ruled out that it's going to be one of the ones that's true, so the rest will be false, or nil as it's called here. Then we get into the parts of this that are the Boolean logic that I was relying on without really saying what I was doing. So obviously, just by the definition of not, we know that not T is going to be nil, and not nil is going to be T. So even though we will cover that in a moment, that's, I think, pretty self-explanatory. Copy those over there. And this is where we get to the identities, right? And nil T. So we could just take the definition of and there, but if we were ever to have just and, nil, and anything, that would still equal nil. So what did I just do there? The technical term for that operation is the law of annulment. You can see here with a little bit of different notation. That up caret is logic notation for and, that down caret is logic notation for or. I'm going to be using the notation that's more familiar in programming languages, but regardless, you can see here, A and false is always false. So that's ultimately the law that I was applying when I did that simplification. And we could go down the list. We've got definition of null. We've got and annulment. We have and t of a becoming a, that is and identity. And these if t and if nil, if true or if false, that is just the definition of if. Now, these simplifications wouldn't all necessarily be correct if there were side effects in some of these expressions and they just also returned a Boolean value. But it so happens in this case we were in a context where we knew we were dealing with pure expressions, as I say. They only produce a value. They do not affect anything outside of them. So we saw this notation where they're doing and or that way, and this little bar is what they're using for not, where we would use an exclamation point, sometimes called a bang, usually in code. But again, I'll be using the more familiar programmer notation today, so you don't have to worry about this right now. I use a lot of these fairly regularly. I don't actually even think of them by their name. They just have become kind of automatic, but they're official names. Annulment, identity, we'll do that one. Idempotence, where a and a or a are both just equal to a. I'm going to do double negation. I'm going to do De Morgan, which is actually my favorite. It's kind of a sleeper hit. May not come up every day, but when it does come up, is very handy. And or, as it turns out, are both associative and they're both commutative. And that means just the same thing as when we say that addition and multiplication are both associative and commutative as well. I don't know if I ever learned absorptive, but I'm going to implement most of these, and it would be trivial to do the others. Once I've mechanized all those laws, I'm going to use them to simplify a complex Boolean expression into a simpler one. And you can see here on booleanalgebra.com, they've got this thing that'll just generate one. So I'm going to use just the first expression that it gave me when I generated it. And they're applying these laws. You can see how they're using them to simplify it. I'm going to do that in my own way. Let's jump into the prover, see how far we get. Now, there was just one more request from the commenter, which was to use dark mode. Now, I actually like dark mode as well, but I normally use light mode on the channel because my impression is that makes the text easier to read in a video. But heck, by request, at least this once, let's go ahead and do the dark mode. Why not? All right, so we're in dark modern. We're in the lean extension of VS Code. And on the right, it's got this thing called Info View, which I'm going to be interacting with as I do this. This would be no fun if I used the built-in Boolean type, because it already knows how to work with that really well. So I'm actually going to define my own Boolean type out of air. So I'm going to use inductive. Now, I'm actually not super experienced with the lean prover, so if anyone out there has used a lot and notices something I could be doing better, feel free to clue us into that. So I'm going to define an inductive type called myBool, and this is going to have a few values. I could call them true and false. I'm going to just, for no risk of clashing with the, standard library here, I'm going to call them T and F. So T is something of type myBool, and F is also something of type myBool. Just like that, I've got my own Boolean type. It doesn't know anything about how it works, but it does know that it has only these two values that type can take. And I'm just going to do one other piece of magic here, which is I'm going to say deriving a representation so that it knows how to print one of these. Except I can't yet because I need to open this type. So it will know when I refer to a value that that's what I'm talking about. Okay, great. Evaluate that expression, it can show it. So we need to be able to do something with this. Now, you can define different sets of the Boolean operations as the fundamental ones. If you really want to, I think you can build them all out of just NAND or out of just NOR. But I'm just going to do the regular thing and define just not, and or. So let's define something called and that is going to take an A and B that are of type myBool. And so what's that going to do? I can use match is a good way to implement this. So if A is either going to be true or false, right? So if it's true, then I should just return B. If it is false, then I should actually return always false, right? So there. That is a perfectly serviceable definition of and. We could try it out real quick if we like. And TT, what is that? Okay, that's T, and T and F is false, and F and T, false as well. Okay, I'm convinced this is a good definition. And we could do or much the same way. So, except in that case, if the first argument is true, then or AB is always true. And if the first one is false, then we return the second element. This is just the definition of this operation. So then the only other one that I'm going to define is not. So not A, and we don't have a second argument. Okay, so not true is false, and not false is true. Great. We could go on if we want to and, define not and, which is NAND, or we could define NOR, which is not OR, but this will do just fine for our purposes today. Now, I'm just going to bring one piece of magic up here, which is that I'm going to, and with the same precedence levels and settings that the core library uses, so there's no clashing, I'm going to define these and or and not operators that we would be familiar with in most programming languages. So now we can use these a little easier. If I say T and F, it knows what I mean. So we've got a mechanized world where we can play with these laws. We really have already given it enough information to know that all these laws are true, because these are not axioms, actually. They are, resultant from the definition of these operations. But we'll go ahead and explicitly define them as laws just so we can be extra sure that they're all true, right? Like, what if De Morgan's was actually not true in some case? Like, De Morgan the Stallion would be furious, I tell you. So I'm going to just start at the top here, and we'll do and annulment. So we've got the word theorem, a theorem name. I should point out there's a little shortcut here that's happening when we've got in braces this A, B, and C of type myBool being defined as variables here. That means implicitly when I say A, that's the type of it. I'm not going to say for every one of these theorems that, oh, for every A and B myBool, that's going to come along for the ride when I reference them. Certainly could define these in every theorem. This is just a little easier. So, and annulment, what is that? That is simply that A and false for any A is equal to false. And you're going to get used to looking at the info view. This is kind of at the heart of what an interactive proof assistant does for you often, is it shows you the state of what it remains to be proven. Right now, it's nothing special because it's just the thing that I asked to be proved. But I'm going to do some operations which are called tactics over the course of this proof, and that's going to change what's happening on the right side here. So I've got this and ultimately this is going to be resultant from the definition of and. So I'm going to unfold that definition, just like inline this function in place in essence, right? Okay, so now my definition that with that match statement of and is just right here in the proof state. If we consider the cases of these, right, we're either going to go in that first case or that second case. If we're in the second case, then we get F out, so we're fine. And again, if we're in the first case, then we get F out, and that is exactly what we need. So we're pretty close to having proven this. So if we do a case analysis on this, which is done with cases tactic, on A, then we will get two, they're called sub-goals, that each match, one of these situations. So here, instead of matching A, we're matching T, because it first gave me the sub-goal where A was T. So happens I can prove that with one of the most basic tactics, which is RFL, means reflexivity. This is not intended as a full introduction to the lean theorem prover, by the way, so it won't be obvious exactly why this or that tactic is the one to use, maybe just from this, but hopefully you at least get a feel from what this is like. In that second case that I haven't covered yet, the same thing will also work. So I no longer have sorry here, which means I haven't proved it yet. Now I actually have proved. Now it so happens if I want to discharge the same tactic on every sub-goal that something has created, then I can use this little operator here. So that's just the same as what we had already. All right, cool. So we've proven the AND annulment law. And what can we do for the OR annulment? Again, that's just A or true is always equal to true for any A. Well, you may guess that simply by unfolding OR and using reflexivity on both cases, again, we get that pretty well. Okay, great. So moving right along, OR identity, A or false is always equal to A. Could it really be that easy? Okay, yeah, we'll prove it just the same way. These will get a little bit more difficult in a moment. So, AND identity, A and T is always equal to A, proven the same way. Now we've got AND De Morgan. So, if you're not recalling De Morgan's law, it exists in both an AND and an OR form, like many of the rest of these. Make the names consistent here. And it's just not the quantity A and B is equal to the quantity not A or not B. As I mentioned, doesn't come up all the time. Super useful when it does come up. So, what can we do here? Well, we're going to at least need to unfold. If we can solve this by unfolding, we'll need to unfold multiple things. So I'm going to unfold both and or, and probably not as well. Do a cases on A, and am I so lucky that I can just do reflexivity on both of them? Yes, I can. Okay, I was worried that I would have to go into a second cases analysis, which would be just fine. But save that for later, I suppose. What about De Morgan's law for OR? Yep. Okay, also proven quite easily. We have AND idempotent. Now, idempotent is kind of a complicated word for a simple concept. It just tends to mean doing something twice is the same as doing it once. And when we're talking about doing things with side effects, that becomes a very interesting concept. In the case of Boolean logic, it just means, A and A is equal to A, or A is equal to A, for example. And I think simply by unfolding and, yeah, we can play the same tricks here. And associative. Now, the quantity A and B, all that and C, is the same as A and the quantity B and C. So in other words, we got a paren grouping here. We can always move that grouping one to the right if we've got a chain of ands or a chain of or, just as you could for addition, for example. Now we have three variables here and not just two. So this one might be more complicated for that reason. Let's see. So first I am going to unfold and, which I guess is the only operation here. And so try just reflexivity by itself? No. Well, at least you have to do a cases on one of them. So do a case analysis on A. Okay. All right, that was enough in this case. Will we get that lucky for the associativity of or? What about the commutativity of and? So A and B is always equal to B and A. That should be fine. So that actually wasn't enough. We are going to have to do something slightly more complicated here. So within this cases of A, on the T case, I will do cases on B, do just a second case analysis. So we're doing a case analysis on the entire state space this can happen. Yeah, because you can iterate over the entire state space of something like this, like these are very easy to prove things about. I'm using a very powerful tool for something so simple, but you know, regardless, it's fun. So then we should be able to use reflexivity. And for this other case, do another case analysis over B, the other case of A, where A is false. Do case analysis over B, and for every one of those, just solve it with reflexivity, and that works. So because we are technically doing the same thing in both these cases, we actually can use that little combinator again, just with some clever parens. That's one way we could do this. There might be others. All right, so or commutativity should be just as easy with an unfold or there. And not, well, that one should be especially easy, right? This is double negation. Not A is equal to A. Well, let's unfold the definition of not. And yeah, is that just enough? Can we do reflexivity there? No, we'll do a case analysis first. All right, great. We've got some little convenience identities here that not T is false, not true is false, and not false is true. That should be obvious, and indeed is obvious to lean prover as well. All right, so now let's apply them in the same way this simplifier is showing here to take a complicated Boolean expression. Indeed, I'm using one that came out the first time I used this thing, and apply those laws on it within the prover. So this theorem here waiting to be proven, we have not the quantity C and B, or not the quantity C and A, that whole thing, and true, not that whole thing, and then or the quantity A and false, right? And ultimately, this entangles into A and B and C, or as it happened to come out, they're C and B and A. You do a bunch of those simplifications via any means you like, applying the laws, draw yourself a Carnot map, look at truth tables, what have you. You will find that that's the same as this much simpler expression. Can we prove it? Of course we can. Now, the first one, I'm going to say we can prove it the same way we have been. We'll just take the shortest path. But that's not the interesting way. The interesting way will be to use these laws. So we'll do that after. So if we just want to brute force this, I'm going to unfold and, or, and not. And we've got this giant mess of match expressions. It's not clear that we've made this better and not worse. From there, again, because the state space is so small, we can just do a case analysis over all of this. So we'll do cases A to break off sub-goals for both the case where A is true and A is false. For each of them, we're going to do the same thing. Ultimately, we're going to break off the cases into further sub-goals on each of those where B is true and false. And can we just... yeah, maybe we can't discharge just yet. So then I'll do a cases on C. And those are the only variables we've got. Discharge reflexivity on each of those. Okay, boom. So we've proven equivalence there by a totally brute force and uninteresting means. but nonetheless, it is proved. There would probably be even smarter and more magic ways of using lean to do this. Feel free to let me know in the comments. But now we're going to do the one that I think is interesting for today, which is to use rewrites based on these laws. So as we look at this, we're just pattern matching. This is just experience, but I'm seeing an and t. So that tells me I ought to be able to use my rewrite rule, the and identity, I believe it was. And so to rewrite using that, we use the name of the theorem in brackets. Yeah, good. I'm also seeing we've got an and false here. So I believe that is and annulment waiting to happen here. Let's see how we do. Yep, I can just combine these into one statement. All right, so and annulment, and I'm seeing an or false, which means we should be able to do an or identity. All right, got rid of that. Now, this here is looking like a situation now that we could probably apply De Morgan's law to. That's right, because notice we've got this, this not quantity C and B, or not this quantity C and A. So if I squint, I'm looking at a not X or not Y. So that should be able to simplify via the or version of De Morgan's. All right, well, it almost simplified. It put just an extra not over it, but that's fine. We can just use our our double negation law. Rewrite on that. Okay, it took care of one instance of that. Let's do a second rewrite using not. All right, we're getting closer. So we've got C and B and the quantity C and A. I want it to be still simpler than that, but we're getting into the vicinity, right? Just by rewriting using rule after rule after rule. How do I get to the destination here? It seems like I've got two C's here. Eventually I want just one C, so I can use that and idempotence if I can get them next to each other, which I should be able to do using some combination of commutativity and associative property, right? If I just do it from here, though, if I just try to apply the rewrite rule blanketly, I'm not sure that it's gonna help me. Let's say I try to do and associative here, right? Okay, what just happened? Okay, it's associating that. That wasn't really the change I wanted it to make. Like, there's any number of things it could be doing here. But there's a way I can dive into the expression and kind of control what I'm going to apply the rewrite rule to. And that is with this cool construct called conv that I learned about yesterday. So I'm going to dive in and say, I'm just interested in the left-hand side of this expression. LHS, left-hand side. Okay. Now, I'm going to try to zoom in a little more. There are different arguments. So if I looked at arg1, it would just be C and B. If I looked at arg2, it would be C and A. If I just tried to apply and associative to the top level, where would that get me? Or I can also apply it in reverse. Now, I feel like that's getting me closer to where I want to be. I think that is an improvement. What's my arg1 look like now? Okay, great. Now I can zoom into arg1 and probably use commutativity on this to rearrange it, because I want to get the C's together so I can cancel them out. That's what I'm trying to do. So if I just rewrite and commutative just right there. Actually, this one I think gets me on my way, because then I can use associativity to move the parens. Yeah, I like this. So I can't rewrite using and associative forwards. Can I do it backwards? Yes. I can. All right, so now what do my arguments look like? Okay, arg1 is just C and C. Perfect. So it seems like I'm all set up then to use and idempotence. There, and now I'm going to step out of this conv. Aha, no more goals. I have indeed gotten them to look identical. That ultimately did what I want. If I took that last one out, you could see after this that I'm right near the end, and I would just have to apply one more rewrite rule, and I'd probably be able to apply it anywhere. It would know where it needs to fit. Yeah. No more goals. So that was a bit of a pain, but we have, the satisfaction, for whatever it's worth, of seeing exactly what laws are being applied there. We got there using strictly rewrite rules. And that is the beauty of a theorem prover. It's very good at using these rewrite rules, not just applying them when you tell them which one to, but also searching the space of what ones it could apply. So let's see what that looks like now. I'm going to now use this special annotation it has, and on all the ones that I want to be automatically searched, these Boolean logic laws, I'm going to put @simp before them all. I'm going to annotate them, saying these should be available to the simplifier. So whenever I try to solve a goal via simplification, they are rewrite rules that it should consider using. It should see if it can get there through some of these rules. So all right, I've added all of those. So let's see how much of this we can get it to do on its own. So in an ideal world, we would just be able to type like simp, and then the simplifier would eliminate all of these. So let's see how far it got. Well, actually not as far as I would have liked, and it's missing some opportunities here. It's missing like false or something should always just be that something. We can get rid of those ors. But do you know why it didn't do that? It didn't know to do that because you actually have to combine two laws to get there, and it probably wasn't obvious that that was actually a useful simplification. I'll show you what I mean here. We're talking about or identity, right? But it doesn't say false or A is equal to A. It says A or false is equal to A. So you combine that with commutativity, and it should mean the same thing. But for convenience here, let's help it along, right? Let's make reverse versions of at least this one, and say this one will be false or A is equal to A. So, or identity reverse, whatever we want to call it. And we could also do and identity reverse. And we see any other convenience theorems we want to define, we can do that later. Now, when you're dealing with something that's commutative, there's probably a better way than just defining extra versions of all the theorems to make it see the other application of it, but I just don't know what that is yet. So let's see. Oh, it goes actually farther now. So that's cool. So yeah, I'd say that got us almost as much as like applying these first 6 laws. It's we're back down to just ands, and it's just like C happens to appear more than once. So we go back to our friend conv here, and I'm going to use it a little differently here. I'm going to just tell it exactly what expression I'm diving in. And I'll go into arg2, for instance, and again I will do a rewrite on and being commutative. And if I just use that associativity here, should be able to dive into C and C and B, rewrite with and associative, and we'll have to apply it in reverse. There we are. Now we seem to be set up to use that simplification for the and idempotence. So is it going to be able to figure it out now? Yes, now Simp can finish solving it. There might be even more sophisticated ways of doing this, but so there you have it. We've just defined our own Boolean type in the lean prover. Using that, we defined our own version of standard Boolean logic operations. We defined as theorems most of the standard laws of Boolean algebra, showing that they follow from the definitions. We showed we could apply those theorems as rewrite rules to simplify an expression on our own, and also that we could give it to the internal simplification engine and have it do it for us. Preparing this episode was my first time using the lean prover. I quite like it so far. If I'm able to find more applications to actual program analysis and refactoring, then you'll surely see more of it here. Until next time, as it says in the Tao Te Ching, with patience, the most tangled cord may be undone. Thank you.